Today we're going to start discussing a new concept that's going to stick around pretty much forever, and that is continuity and what it means for a function to be continuous. So, the mathematical definition for continuity is the limit, a function f is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. Now, what does that mean to you? Well, first of all, it means that f of a is defined, meaning a value exists at a. There has to be a point at a. Secondly, the limit exists. Remember, that means the left-hand limit and the right-hand limit are equal. And thirdly, the limit that we already decided existed in number 2 has to equal that value. So the lastly idea is that the limit equals the value. A layman's way of saying this is if you can draw the function without lifting your pencil, then it's probably continuous. If it's not continuous at a, then we say f is discontinuous. So, what are some types of discontinuities? First one, if we factor this, we get x minus 2, x plus 1, all divided by x minus 2, and if you remember correctly, that means we have a line with a hole at x equals 2. So, our equation is the graph of x plus 1 with a hole at 2 instead of a point. With a hole at 2 instead of a point. That is a discontinuity that we sometimes call a hole. You'll also occasionally see it referred to as removable, because you could put a point in that hole to fix it, is why they consider it removable. Secondly is slightly different. 1 over x squared looks like this. And a point at 1 if x is 0 looks like this. This is considered an infinite discontinuity. And it's infinite because it kind of involves an asymptote. It would be an infinite discontinuity whether this point at 0 was there or not. The point doesn't make a difference, but you couldn't draw that all without lifting your pencil. Therefore, it is a discontinuity called an infinite discontinuity when it involves what appears to be a vertical asymptote. This next one, notice this is the same function from number 1. So we already know what that function looks like. The line of x plus 1 with a hole at 2. And this time they tell us there's the point 2, 1 as the other part of our discontinuity. Now, that is considered a removable discontinuity. There's a hole, there's a point somewhere else. If you notice, the limit is at 3, but the value is at 1, therefore the limit does not equal the value. And finally, a step function. If you remember what a step function is, sometimes called the greatest integer function, you are thinking about what integer is closest to that without going over. So like from 0 through 0.5 up to just below 1, 0 is the integer that is closest to it. When you get to 1, it jumps up to 1, and 1.5's closest integer below it would be a 1. So it begins to look like this, and you can kind of see the pattern, which is why it's called a step function. So that's a step function. And it has multiple discontinuities everywhere where it steps up to another step, and each of those is called a jump discontinuity because it instantly jumps from one value to another. Moving on, definition 2 says a function can be continuous from the right or from the left at a number. For example, the greatest integer function. This function is continuous from the right but not from the left. Let's look at why. If you notice, at all of these steps, if we approach 3, for instance, from the right, the limit equals the value. If we approach it from the left, the limit does not equal the value because the limit is at 2 and the value is at 3. So that's what they mean by it approaching from the right or the left. Our example in our notes talks about 2. If you're approaching 2 from the positive side, you get, I'll put color lines here, you get a 2, but from the negative side, you get a negative 1, you get a 1, meaning both limits exist, but they don't both equal the value. So because the limit as we approach 2 from the positive side equals the value, this would be considered continuous from the right at 2. And the other example, negative 1, would be continuous from the right at 2, not the left. Definition 3, a function can be continuous on an interval if it is continuous at every number in the interval. So, let's look at this. The square root of 1 minus x squared is the top half of a circle. And circle equations are something you should familiarize yourself with. So, they can be continuous on an interval. So, what interval is this function continuous on? And it is continuous from negative 1 to 1. Now, at negative 1, it's only from the right because that's the endpoint, but that's okay. And at 1, it's only from the left because that's an endpoint, and that's okay also, but it would be continuous from negative 1 to 1. Now, a couple more ideas. If f and g are two functions that are continuous at a, and c is a constant, then the following functions are also continuous. If f and g are continuous, their sum is continuous. Their difference is continuous. Each one multiplied by a constant is continuous. Their product is continuous, and their quotient is also continuous as long as the quotient or the function in the denominator does not equal 0. Finally, theorem 5, any polynomial is continuous everywhere. That is continuous on all real numbers. Polynomials are nice smooth curves like roller coasters that don't do loops. And so, they're continuous on all real numbers. So this is a polynomial, no holes, no chumps, nothing weird, means continuous. Now, part B, any rational function is continuous wherever it is defined. That is, it is continuous on its domain. To find the domain of this function, it has a denominator. So x minus 2 is not allowed to equal 0, which means x can't be 2. But it can be everything else. So this would be continuous on its domain of negative infinity to 2 and 2 to infinity. Come with questions tomorrow.